So, now what are the impact does scaling have? So, now let us look at some parasitics, carrier multiplication effect. Okay. Now, what happens? So, this is a very interesting phenomena, which is there is a possibility for positive feedback here which can actually destroy your device. So, if you make the channel length of the device very small, the electric field between the source and the drain starts increasing. Okay. So, this electric field becomes larger and larger. So, let us say we have used constant voltage scaling and we have reduced the channel length of the device. Okay. So, we say constant voltage scaling. Now, this high electric field makes these electrons travel at a very high velocity. So, in fact, the electrons will now be traveling at the saturation velocity. And due to this very high velocity, there is a possibility that these electrons can impact other silicon atoms and can free electrons and holes. Okay. So, you can have impact ionization, they can knock off electrons and holes from silicon atoms. Okay. So, now if an electron and a hole pair is created, if an electron hole pair is created here, the electron would quickly run away, migrate through this and enter the drain. Okay. It will just simply contribute to the IDS. But what does a hole do? The hole sees a p-n junction here. Okay. It sees it sees a p type bulk and an n type drain, that is bulk, and let us say the hole was created here, it is going to run upward and into the bulk. Okay. So, the hole is going to migrate away into the bulk. So, if the hole migrates into the bulk, again if let us say there are several holes and electron pairs created and a lot of these holes start migrating into the bulk, they are essentially going to create a hole current here. So, essentially you are going to have a current flowing inside the bulk, and this current is because of the holes. And the bulk has a certain resistance, okay, because it is doped n type, it is doped p type. So, it is going to have a resistance of a resistivity of 1 by q mu p into Na, okay, and depending on the geometries it is going to have a certain resistance. So, there is a certain resistor here and you are going to have a current flowing through this resistor. And what does this current do? It is going to increase this potential here. So, the larger the current, the larger the potential. Okay. So, essentially we have a whole current flowing through the bulk has some resistance, and therefore, this potential of the bulk begins to increase if this whole current increases. So, if Vb, which is the potential of the bulk, starts to increase, the Vbs starts to increase. And what happens if Vbs starts to increase? If Vb starts to increase, this junction gets forward biased and it is going to reduce the threshold voltage. If Vbs starts to increase, it is going to reduce the threshold voltage, and if you reduce the threshold voltage, you are going to encourage more carriers, more electrons to get in from the source, and this is going to further create more electron hole pairs, and this positive feedback mechanism can simply lead to an instability which will eventually destroy the device. So, there is a possibility of this happening if the device is not very carefully engineered by using correct scaling principles. So, the next parasitic due to scaling is something called as drain induced barrier lowering. Okay. And the idea here is, if you have say a long channel MOSFET. So, here we are looking at band diagrams for long channel MOSFETs. Okay. So, the drain and source are far apart, and the case you are looking here, the case 1 we are looking at is, here you have your source electrode, there is the body, and here is the drain electrode. And if you think of this p-n junction, you have a p-n junction here and you have another p-n junction here. And in order to inject carriers, so this is at equilibrium, this is when there is no VDS applied and there is no VGS applied. Okay. And when we have to when we increase the drain to source voltage, all that happens is that all these barrier heights remain the same, but the drain to source voltage increases, and therefore, you see that this PN junction is now strongly reverse biased. Okay. And when we apply a gate voltage, so this is the case when VGS is still 0, but when VDS is greater than 0. And now when we apply a gate voltage, so when we bring in the gate voltage, when we make VGS greater than 0 and VDS greater than 0, we lower the gate voltage helps to lower this barrier and therefore encourages electrons to come in from the source. So that is the normal operation of a MOSFET. Now when we head towards short channel MOSFETs, okay, the drain starts getting very close to the source. So in fact, if this is the depletion layer of the source, then you can see that drain depletion starts immediately, and that is the band bending. Okay. So the band bending at the condition when VGS is equal to 0 and VDS equal to 0 for a short channel device would look somewhat like this. Of course, I have used straight lines simply because it is easy to draw, but you could imagine a very strong interaction between the depletion region at the drain side and the depletion region at the source side. And without the application of VGS, so this is all at VGS equal to 0 and VDS equal to 0. If VGS is still kept at 0 and VDS is made greater than 0, then what we would expect is a band bending of this kind, as we see in long channel devices. We do not want VDS to actually influence this barrier height near the source side. But since these two depletion regions are so strongly coupled because of the short channel, you see that when VDS is greater than 0, the VDS itself, the VDS field itself influences this barrier height, okay, and this barrier height is lowered because of VDS without VGS being applied, and that is a problem because now what we are doing is we are taking control away from the gate. The VDS itself controls the barrier height, and this is something called as drain induced barrier lowering, where the drain to source voltage lowers the barrier for carrier injection, and you start seeing electrons get in even when VGS is 0. So this is a very significant, in some sense it is a leakage mechanism. It can lead to leakage because if you look at the IV characteristics, so here is an IV characteristics for a very low VDS, okay, and the moment VDS is increased to something that is quite significant, so let us say here the VDS is increased to a larger value, you find that there is significant change in the currents. The device turns on at a different point and it also produces a larger amount of current. So this is something called as drain induced barrier lowering. And in order to alleviate this problem, what happens is how do we get the gate to have more control. So you want to not only have the gate having an interface with just one surface layer, but you come up with architectures such as surround gate or double gate MOSFETs etc. to sort of reduce this impact of the drain and allow the gate to have a significantly larger control on the carrier injection. So with that we cover these topics on the impact of scaling on different parasitics, and we will now look at our studies on the impact of scaling on mobility and then head towards the other topics on MOSFETs. Now with regards to mobility, there are two influences, right. So you have two fields in a MOSFET that control the carrier movement. You have the gate and then you have the source and drain voltages. Now, if the gate voltage is increased, you increase the interaction of these carriers of these electrons with the insulator, and this becomes particularly strong when the insulator thickness is reduced during scaling. And the drain to source voltage also obviously impacts the the movement or the charge transport of the carriers, and at low fields the velocity, the drift velocity of the carriers is defined by the mobility. So, if you remember the plot of drift velocity versus electric field, at low electric fields you have this almost linear relation with the electric field, with the drift velocity being mu times the electric field, and this was the relation that we used to derive the current voltage characteristics of the MOSFET. But in short channel MOSFETs, it is very likely, particularly if say constant field scaling is not deployed, and if you use constant voltage scaling, it is very likely that the velocity saturates because the field is very large. So, the current voltage characteristics is then determined by the saturated drift velocity, that is VD sat, okay, and not so much by the mobility. And in fact, the current voltage relation here, this is the drain to source current, is given by basically the total charge present in the channel into VD sat. Okay, so, this is the charge per unit area into W into length per unit time will determine the current through the drain and source. Now, if the channel length is reduced to such an extent, so if you take your drain and source terminals and you start bringing them closer and closer, okay, so you reduce L to such an extent that L becomes smaller than the mean collision length of the carriers, then we enter into a very different physics of operation. So, what we are saying is that normally these electrons would, when you keep an electron in vacuum, it experiences a force and therefore it accelerates. But in a semiconductor lattice, the electron undergoes all these scattering events. It scatters with the lattice defects, it scatters with the lattice atoms, it scatters with the you have electron scattering, etc. And therefore, because of all these scattering events, we saw that the electron experiences a effective drift velocity, and as the electric field is increased, this drift velocity saturates because the electron is still undergoing these scattering events. But if you reduce the channel length, and these scattering events, you could say that they have a mean collision time of t col and a mean collision length of L collision. If the channel length of the MOSFET, that is if this distance between drain and source is reduced to less than the mean collision length, then it is very likely that a large number of electrons do not on average experience any scattering, okay, and these electrons would simply shoot past without experiencing any scattering. So, we have brought in the channel lengths to within these mean scattering lengths, and therefore, in these regions the electrons could accelerate, and in this case the transport is called as ballistic transport. So, under very high fields, the electrons could move so quickly that they can also enter the oxide. So, you have very high velocity electrons, they have got very high energy, and one consequence of that is you have an insulator here and you have your semiconductor, and these high velocity electrons have got enough energy to get into the oxide, and they essentially become your oxide trapped charges. So, these are all the consequences of having a combination of short channel effect as well as having high fields and their impacts on the mobility of carriers. So, as a final topic with regards to the physics of MOSFETs, let us just look, let us very quickly look at the different mechanisms of leakage currents in MOSFETs. Okay. So, leakage currents in MOSFETs is an exhaustive lecture by in itself, okay, and because we are constrained with regards to time, we cannot talk about this so exhaustively, but although we will touch upon certain topics, particularly things like space charge limited current, we will have a special lecture on that, but as such we will only spend this one slide on understanding the different mechanisms of leakage currents in MOSFET. Now, firstly, why are leakage currents, why is the study of leakage currents so important? It is important because when you have a MOSFET and when the MOSFET, when let us say you have a n channel MOSFET, when VGS is greater than VT, the MOSFET is said to be on and you are supposed to have a current through the MOSFET, and when VGS is less than VT, we technically want the MOSFET to be turned off. We want all the currents in the MOSFET to be as low as possible. But in reality that is not the case. Okay. We do have leakage mechanisms. You do have a leakage of charge between the drain to source even when VGS is less than VT, and these mechanisms contribute to leakage currents. So, what are the different leakage mechanisms? So, first let us look at leakage through the gate. Okay. Now, if you look at gates, if you look at the insulator was in place to make sure that the input resistance to the MOSFET was theoretically infinite, at least at low frequencies. Okay. But in reality you do have the insulator leaking charge. You do have a small amount of current from the gate to the semiconductor. So, what are the mechanisms by which a current can exist through this insulator? The first mechanism is something called as space charge limited currents. It is a drift driven charge transport, but it is called space charge limited because depending on your structure, okay, so depending on the trap state density inside the insulator, or depending on the quality of the insulator, you could have different mechanisms of transport where the transport is limited by space charge, which is in this case the electrons themselves. Okay, so the idea is this: you have an electric field across say two plates and you inject a lot of electrons inside. Okay. Now, what is the electric field felt by an electron here and what is the electric field felt by an electron here? Now, if there was only one electron present in this region, we would say that the electron experiences a certain field and therefore it has got a certain drift velocity. So, if this is a semiconductor, it has got a certain drift velocity which is mu times the electric field, and this contributes to the current. But on the other hand, if there are several electrons present and these electrons form a very sparse pathway between these two terminals, then you need to solve Poisson's equation here. Okay, you need to write Poisson's equation in that region to say that the electric field distribution in that region is defined by the charge distribution in that region, and therefore not all electrons will see the same field, and therefore this current is determined by the space charge, which is basically this charge distribution in this region, and therefore it is something called a space charge limited current. Now, we will have a special lecture that identifies different means or mechanisms and models for space charge limited currents, but this is one of the methods of charge transport through the insulator. The other method that you are familiar with is tunneling. So, as we saw, since the insulator is a barrier, okay, so let us say you have your metal semiconductor. Okay, let us say we have turned off the MOSFET. So, the gate voltage is 0 or less than 0 and the MOSFET is supposed to be technically off. Okay, but you still have electrons. These electron wave functions can exist inside can penetrate this barrier, and these electrons can appear on the other side, and therefore this leads to a current through the insulator, and that is due to tunneling. So, this is another mechanism of charge transport through the insulator. The next is something called as hopping, and this is again something, a topic that we will briefly talk about when we have a lecture on disordered semiconductors. So, the idea is you have an insulator, and let us say the insulator is defective. So, you actually have energy states inside the band gap of the insulator, and these energy states can act as little homes for electrons or for any carriers, and the carriers can hop between these energy states, and this hopping can be encouraged by the field, and it is determined by the energy level differences between these states as well as the spatial distances between these states. So, there are many mechanisms that determine hopping. Okay. So, that is another mechanism of charge transport through the insulator. And finally, you have mobile ions which can also contribute to gate currents. So, these are the different mechanisms through which you have currents through the insulator. Now, when we scale down the MOSFET, the idea is to scale down W, L as well as Tox. And when the thickness of the oxide is scaled down by a factor of K, mechanisms such as tunneling and space charge limited currents are all supposed to increase, and they will increase quite significantly. Okay. So, what is the option? Okay. So, we want to improve field effect, which means if you look at your current voltage relation, where you have mu Cox W over L into say VGS minus VT square, we would like to improve this parameter here, which is Cox, and we are attempting to do that by performing scaling. So, we have Cox is epsilon ox by Tox, and you scale down Tox and therefore scale up Cox. But scaling down Tox will result in these leakages. Okay. And how do we overcome that? We say that we do not scale down Tox all the way. We instead pick a dielectric which has got, pick an insulator which has got a high permittivity, and we improve epsilon ox and therefore improve Cox, while trying to keep Tox the same or while trying to scale down Tox just a little bit. Okay. And in this way we can still improve your field effect and at the same time not given to all these gate leakage mechanisms. Now, the gate leakage mechanisms effectively reduce the input impedance. They do not keep the input impedance infinite, and they make it quite finite. Okay. And this has got implications when we design circuits. Now, what about leakage mechanisms between the drain and source? So, you have the drain and source electrodes in a MOSFET, and when the MOSFET is off, okay, when the gate voltage is supposed to be less than Vt, the idea is you do not have an inversion layer formed. So, there is no inversion layer when the MOSFET is off, and theoretically we would like that the current be 0. Okay. Or in other words, if you remember the switch or sending a signal from A to B, when the switch is open, we would like the resistance of this MOSFET or this switch to be ideally infinite. Okay. So, which means that you do have a drain to source voltage, there is a VDS that is greater than 0. If VDS is 0 and if VGS is 0, there should be no current in the MOSFET, there is nothing driving any current mechanism. But if VDS is greater than 0 and VGS is less than VT, or if you keep the VGS at a point where the MOSFET is supposed to be turned off, then we do hope that the current is 0, but that is definitely not the case, and that is because of many leakage mechanisms through the transistor between drain and source. So, what are the different leakage mechanisms? The very first, and in fact the most significant, is subthreshold leakage. So, we have already seen that when VGS lies in this region, VFB less than VGS less than VT, we have a few carriers injected in the near the source side, and these carriers diffuse over to the drain side, and we have something called as the subthreshold conduction, and we looked at this in some detail and we defined the subthreshold slope, etc. So, that becomes one of the leakage mechanisms. Okay. You do have subthreshold currents. Now, apart from that, let us take a look at the drain bulk interface. Okay. So, you have the drain, you have the body of the semiconductor, okay, and you have this p-n junction which has got a band bending of this sort. So, all leakage mechanisms, okay, and this p-n junction is reverse biased, okay, and near the source side it is not, depending on the body to source potential. Now, all mechanisms that contribute to currents in a p-n junction also contribute to currents in a MOSFET that is turned off, okay. And what are those mechanisms? You do have diffusion across from the p type body and the n type drain. So, you do have diffusion currents, and in the depletion region you will have a generation of electrons and holes, because the depletion region encourages generation in a reverse bias p-n junction diode, and therefore, these electrons will now drift over to the drain side and these holes will drift over to the body. And then you do have something called as band to band tunneling, which is essentially the tunneling of carriers from the p side to the n side, okay. So, these are, that is another mechanism, okay. And finally, you have something called as gate induced drain leakage, okay. Now, this is something that you are probably hearing for the first time, okay. So, what is gate induced drain leakage? So, let us take the condition when Vg is less than 0 and Vd is greater than 0, and let us now focus on the gate drain overlap region. So, you have your p type body here and the gate is negative, or it is turned off, let us say. So, the gate voltage is kept at less than Vt, and essentially it is much lower than the drain voltage, and you have a Vd that is greater than 0, okay. And the hope is that there are no leakage currents through the source and drain. But if you watch the gate insulator gate insulator n type semiconductor region, okay, what you have is a metal insulator semiconductor contact, and with the metal having a lower potential. So, this would lead to several depletion regions. So, firstly you have the depletion region on the p side and the n side here, because of this p-n junction diode between the body and the n doped drain, and then you will now also have a depletion region that exists in below this gate, and any carriers generated or any carriers present here will drift through all these electric fields, okay. So, you will have all the electrons, okay. So, if you look at this depletion region, it looks like that. So, all the electrons will now start running away to the drain side, and all the holes will now start running away to the body, and this causes another leakage mechanism. And so, these are basically carriers that are present under the gate overlap, okay. So, it is the same basically the same mechanisms that would contribute to depletion, the currents due to depletion regions in this p-n junction diode, but the only thing is this depletion we are talking about is now under the gate overlap region, and it is because of the gate drain field, okay. So, this is something called as gate induced drain leakage, okay, and that too leads to a small leakage current. So, normally without gate induced drain leakage your currents should be somewhere else, and with gate induced drain leakage your currents are a little higher. So, you are basically having leakage. Now, why are we so worried about leakage? So, firstly it completes our MOSFET models, right. So, we looked at, let us draw the IDS VGS characteristics of a MOSFET. So, we now have a characteristic which is actually very well drawn here. So if you look at this characteristic, we initially had defined models for only the above threshold region, which is all your square law characteristics. We then refined the model to define the subthreshold region, where you have this exponential dependence on VGS, and that is why a log ID. So, if you look at this, it is a log scale. The log ID versus VGS characteristics show a straight line in the subthreshold region. It is a straight line. And now we are going one step further and refining the model by defining all the leakage mechanisms in the MOSFET. So, you have leakage through the gate and insulator, and you also have leakage from source to drain. And all these leakage mechanisms are important because they contribute to power, the loss of battery life. So, for example, if you are using these MOSFETs in circuits, okay, and let us say you have a circuit and this MOSFET is supposed to be turned off. Okay, so, we think the MOSFET is turned off and there is supposed to be zero current, or we hope that there is zero current despite the MOSFET being connected to a power supply. And therefore, we expect that the power consumption of the MOSFET when it is turned off is the VDD into the current through the MOSFET, which is 0. But because you now have a leakage current, since I is not 0 and you have all these leakage mechanisms, you have static power consumption in a MOSFET circuit, and this power consumption exists even when all the MOSFETs are turned off, and this is going to drain the battery charge because it is going to continuously drain this much of power from the battery. It is going to drain this much of charge from this much of energy from the battery at this power. So, therefore, leakage is important, and as I said, this is all we will talk about with regards to leakage, because this itself could form an entire chapter or a detailed set of lectures by itself, but we are short on time.